The Wolfram language includes lots of functions for doing algebra and calculus and other calculations in symbolic mathematics. To start with a few examples, this shows the solve function computing symbolic solutions of an equation. This shows the simplify function doing symbolic algebra and applying trigonometric identities to find a simpler form of an expression. Also, most linear algebra functions can handle matrices with symbolic matrix elements. For example, this uses the eigenvalues function to compute the eigenvalues of a symbolic matrix. There are also functions for doing symbolic calculus. Symbolic differentiation, for example, can be done using the d function. Symbolic integration can be done using the integrate function. This shows integrate giving a result for an indefinite integral. And it's also possible to get symbolic solutions of differential equations. This shows the dsolve function finding the solution to a simple differential equation with an initial condition. The availability of a function for doing something on the computer usually depends on the availability of a suitable algorithm. This evaluation, for example, which shows the rsolve function giving a closed-form solution for a recurrence equation, is available because computer algorithms have been developed for solving a broad range of recurrence equations. Another example is the Boolean convert function, shown here converting a symbolic Boolean expression into a special form called disjunctive normal form. The Boolean convert function is also available because there is a process for doing this sort of thing that can be programmed on the computer. It is also often possible to get useful results even when there is not a comprehensive algorithm or when the result is hard to specify. A good example of that is simplification of expressions, where there are typically many possible results. This input, for example, shows the simplify function converting a trigonometric expression to a form that is arguably simpler, but there are many other possible results. For example, this shows a result obtained by applying trig_expand to that same expression. This shows the result from the trig factor function, and this shows yet another possibility, this time using the simplify function with a non-default setting for the complexity function option, which is used to specify which forms should be considered simpler. These or other forms for the result could be useful in different situations, but since it can be difficult to specify the desired form, it can be difficult to get the computer to return a specific form automatically. Another interesting example is showing the steps in a calculation. Here, for example, is an integral where we might want to know how this integral was computed. One way to see some of the steps in one method of doing this integral is by entering the integral into Wolfram Alpha. The display from Wolfram Alpha includes a button labeled Step-by-Step Solution that can be clicked to show some of the steps in one method of getting this result. But there are other methods of getting the same result, and the method actually used by the computer involves many millions of small steps, and there isn't an obvious way to specify which of those millions of steps should be shown. But the result that is shown can still be quite useful. Many symbolic calculations depend on properties of symbolic parameters. For example, the square root of x squared could be simplified to x if it is known that x is positive, but without that assumption, the simplify function leaves the square root of x squared unchanged. The assumption that x is positive can be included in the second argument of simplify. Assumptions about symbolic parameters can also occur in output. Here, for example, is a result from solve with solutions for a quadratic equation. The special symbol reals is included as the third argument in solve to specify that the symbols x and g in the equation and the solution are real numbers. The solution is expressed in terms of conditional expressions. The first argument in conditional expression gives the solution, and the second argument gives any conditions on that solution. In this example, for the solution to be a real number, the parameter g must be larger than -1, so that condition is included in the second argument of each conditional expression. Here is another example, this time involving simplification. Since the cosine function in that example is periodic with period 2 pi, the expression cosine of x plus 2n pi could be simplified to cosine of x if n is known to be an integer, which can be specified by including element n comma integers as the second argument in simplify. In mathematical terminologies, integers and the specification reals from the previous example are called domain specifications. The traditional mathematical notation for specifying that n is in the domain of integers uses the element symbol and a symbol that looks like a z, which is the traditional notation for the integer domain. That notation can also be used in the input to the simplify function. Domain specifications can also occur in output. Here is a result from solve where the solution is that n can be any integer. The notion that n can be any integer is represented in that result using a conditional expression in which the first argument is a parameter c1 that is introduced for the purpose of representing the solution, and the second argument specifies that c1 be in the domain of integers. Some symbolic functions return generic solutions that are only correct for generic or typical values of the parameters. For example, this shows an infinite sum where the result is correct for values of x that commonly come up in applications, but this sum actually will only converge if the absolute value of x is less than 1. The sum function can be made to include that condition in the result by setting the generate conditions option to true. The result is again a conditional expression that includes the condition on the symbolic parameter x. In addition to conditional expressions, there are several other special structures that occur in symbolic calculations. One example is a root expression, such as the root expressions in this result from the solve function. Root expressions are used for representing numbers that occur as roots of polynomials. Root expressions can be used in calculations much like other symbolic expressions. For example, this shows a plot of the absolute values of those solutions as a function of the parameter b. In applications, mathematics is often done numerically rather than symbolically, but symbolic analysis can nevertheless be quite useful even when results are ultimately computed by numerical methods. In the Wolfram language, many numerical functions do some symbolic analysis automatically. One such function is the n-integrate function, shown here doing a numerical integral. A plot of the integrand in this example shows that the integrand has many oscillations over the range of integration. In this example, before doing the numerical calculation, the n-integrate function actually does some symbolic calculations to recognize the oscillatory nature of the integrand and transform the integral to a form that gives more accurate results for oscillatory integrands. In a purely numerical system, that symbolic analysis would not have been possible. In a purely numerical system, the integrand is typically specified using a separate function or subroutine like this one. The n-integrate function can still attempt the integral but gives an error message and an incorrect result. With this separate function as the integrand, which is used only for giving numerical values of the integrand, the n-integrate function has no opportunity to do any symbolic analysis to choose a suitable algorithm. This particular integral can also be done entirely symbolically using the integrate function. Numerical evaluation of a symbolic result like this is often provides for faster and more accurate calculations than doing the calculation numerically. When some part of a calculation can be done either symbolically or numerically, there are typically trade-offs to consider involving speed or memory or accuracy. For one last example, here is a simple matrix calculation involving a symbolic parameter b. A numerical result can be obtained by inserting a numerical value for the parameter in that symbolic expression. The same result could also have been obtained by including that numerical value in the original matrix and doing the entire calculation numerically. In this example, the purely numerical calculation is faster and uses less computer memory, primarily by avoiding the symbolic calculation and the need to construct a relatively large symbolic expression as an intermediate result. A single number, after all, does not use very much memory. If this calculation is to be repeated for many values of the parameter, however, then the symbolic calculation may offer some advantages. These two inputs, for example, show a speed comparison for a plot of the symbolic result as a function of that parameter and an equivalent plot constructed by a purely numerical calculation. The plot done by substituting numbers into the symbolic expression is slightly faster in this example than the purely numerical calculation. The results from comparisons like these depend strongly on the details of individual examples, but there are still many situations where symbolic analysis can greatly improve the performance of otherwise numerical calculations. Good sources in the Wolfram documentation for more information on symbolic mathematics include links from this page on algebraic calculations and pages on selected topics in mathematics, such as this page on manipulating equations and inequalities and this page on calculus.